let's get started. And we are going to start with a couple clicker questions here. So number one, what does Kepler's second law imply? Remember I said there's one thing that is important to me. Whoops, not that. Just trying to move that you remember about Kepler's second law.
An object that stays in motion.
You're not supposed to say it out loud, but no, that's Newton's first law of it. Channel 33 or session ID web ASTR.
Is Kepler putting in the star like?
Yes.
No, this one. First time.
Channel 33. Okay. Yuri and Jessica. Yari, sorry, Yari. Jessica. Hey, Tim. Okay, and what we got here were 8 people who said this, and 1 person that said that. And let's go to the cards. This person here is not here.
I'll do it.
It can't be you because you and Russell are the ones.
Then I'll volunteer. How about that?
No. Chioni. Well, I'm not going to call him Chioni because he wasn't here when we asked the question. I know you want to. Jessica. Oh, it's not that mean to go through. So, Jessica, give us your answer and your reasoning.
I was thinking it was the one, but I had in mind that the planets don't like move in circles around the sun, and so I was like, oh, probably it's not like close to the sun.
Okay. The Kepler has 3 laws, and the first law is that the planets do ellipses around the sun, with the sun as one of the focal points. The second law is the one that has the area swept out per time from the line going from the sun to the planet is constant. Which all I want you to get out of that is, that's the question, it goes faster when it's closer to the sun, because when it's closer, it has to go a bigger distance to sweep out the same area. Slower when it's farther away. And then the third law was the one that relates the time to do a complete orbit to how far away it is from the sun. The third one has the equation that is the period in years squared is equal to the semi-major axis in astronomical units cubed. Do you remember what term I used for semi-major axis when I first said this law?
It's just the distance to the center of the ellipse, but I don't know if that was the term.
Okay, what I called it was the average radius. It's the average radius for going from the sun to the planet is another name for that semi-major axis. All right, next question. Get more people this time because more people have arrived. And remember, it's channel 33. The diagram below illustrates a portion of the model for the universe described by, and all of these names are famous astronomers, or famous in astronomy, I should say. Aristotle is probably not so much a famous astronomer as a famous thinker.
register like 2 hours ago and still not working.
I checked 10 minutes ago. It said you weren't registered. So if you want after class, we will work on it. Yeah, that's right. If you're not using Clicker, you can't answer until you have it registered. Okay, so still waiting for Jessica. Okay, we have 0, 2, 5, 2, 1. All right, I'm going to have you turn to a neighbor and discuss with them what you answered. If everyone that's a neighbor answered the same, find somebody who answered different so you get a competing point of view.
Just because that's what I
Yeah.
I don't know.
It's definitely not.
So why is
I really didn't want to answer it this time because I'm pretty sure I got it wrong. No, I knew it wasn't what I answered. Why did I do that? I meant to answer 3.
What did you put?
I put 4.
Okay, you guys ready to try this again? Okay, go ahead and answer again. After you've discussed with people. And Daniel, you are the person who Aldwin chose. I was telling Daniel he's the one that you chose. I had him cut the deck.
Oh, I explained my answer?
Yeah, but first Jessica has to get her answer. Okay, so after further review, we have... Okay, go for it, Daniel.
Well, I remember you talking about this in the last lecture.
Mm-hmm.
I was debating between 2 or 3. I wasn't too sure about it, but it was mostly an educated guess based on what I remember from you talking about.
What specifically gave you what you remember from the last one? What aspect reminded you of the idea that was told me?
Because I just remember that name being mentioned last.
Okay, Ptolemy is the right answer. Ptolemy is the right answer because he's the one that introduced these epicycles, these circles that the planets are doing, not just going on a sphere. Aristotle had the planets on a sphere just doing circles. And Ptolemy had circles in circles, like the spirograph I said in class. And of course, I like this picture because it illustrates how you have to have Mercury and Venus pinned to the line going between the sun and the earth to keep them from having elongations beyond 27 and 27, 48. I think I'm getting closer on the numbers. Question.
How did he explain, like, the epicycles, the orbit of the epicycles? Because, I mean, maybe I'm assuming they knew this information then that we know today, that to orbit around something, you have to orbit around something. There has to be some matter in the middle. So how did what did he say was in the middle that they were orbiting?
That is a really good question, and there is no answer. That was back in the day when, if it made sense to you, it was considered good. There wasn't the why to it.
Okay.
And so, why did Aristotle have spheres? Because he thought they were the perfect shape. Why were they made of crystal? Because he thought it was the perfect material. It wasn't based on, and we have evidence for it. It was, I thought that was a good idea. And so what Ptolemy did was he took the sphere idea and he just added another one to it. Why? I like this just because.
Why is it so fuzzy?
Hey, it looks perfectly clear to me. What about you guys? Okay, we'll stop messing with you. I don't know why it's fuzzy. It wasn't fuzzy last time I looked at it. Since he just got his glasses, I thought it'd be funny to mess with him. Sorry. Okay.
My eyes on about that.
So
Everything else is clear except for the screen.
yeah. So this gives us some perspective about how, over time, knowledge was developed in astronomy. So you see here that Copernicus was essentially living the same time as Michelangelo and Luther.
And Vinci.
Yeah, overlapping with Da Vinci and Columbus there. So Copernicus was, we always have separate historical things in our mind. At least I did. I can talk about the Reformation, have my timeline there. I can talk about science and have my timeline there. And I don't think about how the two were related, how the world itself is at those times. And you see Copernicus popularized again the geocentric model, but people didn't accept it. And then we have Tycho Brahe, who essentially was born right after Copernicus died. Now, Tycho was not pushing a heliocentric model, a model with things going around the sun, but he hired Johannes Kepler. Johannes Kepler and Galileo, they overlapped. Galileo was born first, died last of those two. So they were working at the same time. And it was Kepler who actually has the reasons for people to believe that we have the sun at the center. Yes?
Can you remind me again who was it that had the model where everything was orbiting around the sun, but the sun was orbiting around the Earth? Where the Earth and the sun were orbiting around each other, but then everything was orbiting around the sun because you couldn't see parallax or whatever? Was it Copernicus or?
I don't remember anyone with that set of beliefs. I know Tycho Brahe had a really bizarre model, so it could have been his. But the ones I have talked about were basically Aristotle, everything's going around the Earth, told me that the Earth is a little bit offset from the center of the universe and that everything is orbiting an equal amount offset from the center on the other side of the center, which that was another thing to help with the retrograde motion, and it had the epicycles. And then we have Copernicus, circular orbits around the sun, Kepler, elliptical orbits around the sun. Those are the ones that I've talked about. And you see here, Shakespeare was a contemporary of Galileo. Guy Fawkes, however you pronounce it, was about that same time. He's been made very famous, V for Vendetta. And yeah, Queen Elizabeth, Rembrandt here. It's interesting to me. And then we have the person who we physicists put on a very high pedestal, Sir Isaac Newton, who was born the year Galileo died. Now, looking at some important dates there, 1609 is when Kepler came out with his first two laws. His first two laws that gave very good fits to the motions of the planets. And then Newton, over 60 years later, he came out with his ideas that gave a reason for Kepler's ideas to be correct. So that's where we first have the reason. You asked, why did Ptolemy come up with that? Don't really have an answer. Kepler came up with his based on observation. So his was based on data and fitting a pattern, but not knowing why. And for physicists, seeing a pattern and not knowing why is really unfulfilling. And of course, he died that way. But Newton was the one that gave scientists a reason why. And Newton's work was adopted almost instantly because also you have a reason why for something everybody had accepted already. And so today's going to focus on Sir Isaac Newton. And of course, I love that we have Blackbeard and William Penn, two people that we think of in completely different circles from Newton, but they were all contemporary. So, if Newton had gone in a different direction, he could have been a pirate out there with Blackbeard. Could have happened. Yeah, or he could have been a colonist. He could have been here in the U.S. of A. All right.
Why would you want to do that?
Yeah.
There's nothing to do.
Moving forward, getting into Sir Isaac Newton. Now, Sir Isaac Newton, did I already talk about Newton like the first or second lecture about his father dying?
No.
Okay, well then I'll tell you the story. I thought I did. Okay, well, I'll just tell you again.
Maybe you spoke about it in physics.
I could have, yes. Okay, so Isaac Newton, when he was born, his father died. I think his father actually died before he was born. It was sometime, very, very young. And his mother remarried when he was just a little tot, like 2. And she married some guy who worked in the church. And this guy was such a kind, warm-hearted man. And he said, I married you, sweetie, but that kid ain't mine. He's not going to come live with me. And so he was raised by his grandmother. And through his formative education, he did what lots of people do. He paid no attention to the teachers. The teachers are up there droning on, much like I'm doing. And he was trying to make little inventions to impress the girls or, thinking about other things. And so when he got done with, I think it was 6th grade, the compulsory education portion, they said, well, obviously school is not the place for this guy. He's just wasting everybody's time being a nuisance. So he got a job as a shepherd. And as a shepherd, you really have just one responsibility, right? You watch those sheep. But he did just like he did in school. He sat there and made his little inventions. And so he was a failure as a shepherd because he didn't pay attention to the sheep. And so people said, okay, this kid is clearly brilliant. We need to find a way for him to get educated. So people put together money. He went on to higher education, where he still kind of goofed off until his last year when he realized, if I keep on this trajectory, they're going to make me work again. And so his final year, he turned it on, got hired as a house scientist for one of the professors, which is kind of like a graduate student. And then the greatest thing that ever happened to Newton occurred: the Black Plague. Because when the Black Plague occurs, you have people dying, and the people living with them are dying. And you don't want all of the young, brightest minds all together so they can all die together. You want to separate them so you have, maybe a few of them will die, but they won't make all the rest of them die. And so school was canceled for almost 2 years. And so Newton went back to his grandmother's house. And while at his grandmother's house, if it was me, I make it very clear, I would have just gone to my sister's house in Huntington Beach, right? Wake up at noon, amble down to the beach, hang out for a while, amble back home, one more day, right? But no, he said, sweet mother of Mary, I can devote my entire time to physics now without having to do any of these other things. And so during that time, he started thinking about things, and he came up with 3 laws of motion that we're going to go through here. And he came up with an understanding of how gravity works. Before that, people thought the only way I could ever put a force on Russell is if I touch him. If I lay hands on him, I put a force on him. Force is anything that pushes or pulls. So if I touch him, right, I put a force on him. But here, I can't do anything to him. I have to actually touch him. Well, Newton came up with the idea that you have an apple up there in the tree, and when it breaks free from the tree, it doesn't just hover there, it falls down, which means something is pulling it down. So there's something pulling on it, even though nothing's touching it. And then he went further to think about the moon, but he came up with the idea of gravity. And in order to actually work with his new laws in gravity, he had to invent a new kind of math that we call calculus. Now, the calculus, there is debate about who developed calculus, because he'd come up with this new map of fluxions, and a French mathematician came and asked him about it, and he explained it to him. That French mathematician went back and he wrote an article about calculus. And Newton had never written an article about calculus, and so the first person to publish about it was the French guy. And so that's why there is contention about who really invented it. The one who came up with the idea first, or the one who published it first. But at any rate, he's usually the one that we English speakers give credit for inventing calculus. All in that 18-month, he also did some work on optics during that time. All in the 18-month period because there was no school. Yeah.
Apparently, I think it was like Archimedes had written like the first book detailing the principles of calculus, but then a monk overread it.
Okay, I don't know about that, so I can't argue either way. You know more about history than I do. I'll give you that, Russell. I'm impressed.
So yeah, calculus was also history.
So, moving on with, by the way, yes, there's a pretty picture of Newton. He was also, for a short time, a politician. As far as I've been able to read, he went on record once. He's on record once for speaking in the House of Lords or whatever he was in.
Oh, so he had a maiden speech.
No,
That's
He
the
got-
first time speaking is a maiden speech.
he got up and there was all, ooh, what's he going to say? And he said, could we close that window? It's a bit drafty in here. I don't think that counts as a main speech. So he wasn't much of a politician. He did write extensively on religion. He wrote about as much on religion as he did on science. He was very strongly devoted to his religious ideas. And he wrote Bible commentaries. I've not read them. I've not read Ellen White's either, but I'm told that they're very similar. Yeah, I've read parts of Ellen White's commentaries, but... Okay, so turning to some physics stuff. The rest of today's lecture is straight physics, which of course is my area of expertise, not so much yours. So we have to have some terminology, and the first one is acceleration. Now, we probably all drive cars, and we have a pedal in the car we call the accelerator. And what happens when you press on the accelerator?
You go faster.
You go faster, as long as you have a car that works appropriately. I used to have this Toyota Camry. When I pressed the accelerator, it would slow down for a second or two, and then it would go faster.
But it ended faster.
In the end, faster, yes.
Unless you have a stick shift.
You put it in neutral, you press the accelerator, nothing happens. Okay. Acceleration is defined as the rate at which the velocity changes. And velocity is another word. A lot of people have kind of a sense of velocity, but not the real essence of it. Velocity is speed and direction. So if I tell you I am driving down the freeway at 80 miles an hour, I'm giving you a speed because I didn't tell you the direction. If I tell you I am driving down the freeway due west at 80 miles an hour, then I've given you a velocity. And yeah, if I tell you I'm driving down the freeway due west at 80 miles an hour, you can know in 22 hours I'm going to be in Lincoln, California, right? That's about how long it takes to go from Lincoln, Nebraska to Lincoln, California. So, acceleration is anything that changes that velocity. Obviously, changing your speed is changing your velocity. So, acceleration changes your speed. But also, turning changes your velocity because you change the direction. So, in your car, the steering wheel is also an accelerator because by changing direction, you're accelerating. And of course, the brake is also an accelerator because when you brake, you change your speed. So in your car, the steering wheel, the brake, and the accelerator, those are all things that cause acceleration. So acceleration, anything that changes velocity, and acceleration tells us about how quickly the velocity is changing. High acceleration means that you are changing speed rapidly or changing direction rapidly. That direction part is going to be really important to us in astronomy. Okay, force, I've already talked about, something that pushes or pulls. So right now, is there anything pushing or pulling on me?
Gravity.
Gravity. Gravity between me and the center of the earth is pulling me down. That was one of Newton's discoveries. Before him, we had Aristotle, who simply said there's a natural position for things. Aristotle believed that the whole universe was made up of the earth was made up of 4 elements. Things outside the earth had a 5th element called the quintessence. And so those 4 elements were earth, water, air, and fire. And earth has a natural position. Her pen just fell to the earth. That's the natural position for earth, according to Aristotle. And water has a natural position because he saw water on the surface of the earth. So he said water's natural position is just above the earth. And air's natural position is just above the water. And fire's natural position, because when you have fire, the flames go up, must be up above the air. And so I believe everything was made up of just these 4 elements, and depending on how much of each it had a different location that it would want to find itself. And the more earth it has, the faster it's going to fall and hit the ground. That's what Aristotle believed. And it wasn't until we had Galileo and later Newton that we got to our present understanding of, no, there's this force of gravity that points down. It's not a natural motion that things need to fall. It's that there's a force of gravity that pulls them downward and makes them fall. So right now I have a force of gravity pulling me down. But I'm not moving down. There's got to be another force. What's that other force? Now, it is the force I'm looking for is a result of the electric force, but we call it the normal force. Normal is a direction in science. It's the direction coming out of the surface. So here's the tabletop. The normal direction is coming straight up out of it. For this covered side, the normal direction is straight out of it. So the normal force is the force that is coming straight out of the surface, not allowing something to go through it. And that normal force results because the electrostatic bonds, or electromagnetic bonds, between atoms are holding them together so they can't separate for something to go between. So that's what forces are, things that pull or pull. Gravity is the big one we're going to talk about, but Newton came up with some laws to help understand forces. And so Newton's 3 laws. The first law, which when you learn the second law is forgettable, that's why that's the second law. The first law, I think Aldwin already referred to it. An object in motion stays in motion unless acted on by a net force. Now, what that means is, if I have an object that's moving like this, it's going to stay at constant velocity. So it's going to stay in the same direction at the same speed unless something pushes or pulls it to make it change its motion. That's the first of Newton's 3 laws. Question, Russell?
Like how the spacecraft work?
Like what?
Spacecraft work?
Yes, if you get away from any gravitational objects. Right. The fact is, it's pretty hard to get away from gravitational force, but we think about it like they do. So that's Newton's first law. It basically says things will have a constant velocity unless there's a force acting on them. Going back to Aristotle had said that the natural motion is to be at rest in the natural position. So Aristotle said, I have this remote, its natural motion is at rest. If I push it, that was unnatural. And it comes back to its natural motion of stopping. And Galileo was the one who said, well, there's something making it stop. And Newton was the one who made the rule, the law, that says, yes, there must be a force that's making it stop. And the second law, which is super important in all of physics and astronomy, says the net force on an object is equal to its mass times its acceleration. Or the acceleration of an object is equal to the net force acting on it divided by its mass. Well, it's a little frustrating because every time I move a step forward, there's another jargon term we have to introduce. I have introduced acceleration today. I've introduced force today. I've introduced velocity today. Now we have yet another one, mass. Mass is a measurement of how much stuff is present. So something with a large mass has a lot of stuff present. Something with a low mass doesn't have much present. And so I have a fairly large mass. You can figure that out just by looking. A lot of people get confused between mass and weight. Because you look at me and say, well, there's a lot of him. He must weigh a lot. And that's a true statement. But if I were to go to the moon, there would still be a lot of me. But I would weigh 1/6 as much. Because the force of gravity between me and the moon would be 1/6 as big as the force of gravity between me and the earth. And weight is the force that I am pressing down on the ground with. So on the moon, I would have 1/6 the weight, but still the same mass because I still have the same amount of matter in me.
Would
Question?
you be the same in kilos?
I would be yes, because kilograms are the units of mass. In fact, I'm glad you brought that up. I didn't talk about the units of any of these, and it's really, when you talk about these variables, you also have to know what their units are. So, variables we had. Let's start with velocity. Here's a fun little piece of nomenclature. V is equal to the speed. V with a bar over it, an arrow over it, is the velocity. What was the difference of speed and velocity? Velocity has direction. So that arrow on the top indicates it has direction. We call that a vector if it has direction. The units of those two are units of distance over time, meters and seconds, because the definition of speed was change in position. Delta. I haven't defined delta yet, have I? That triangle is the Greek capital delta, and it means the final value minus the initial value. Or as we often say, the change in. So if I read V equals delta X over delta T, in my brain, I read speed is the change in position divided by the change in time. I know this is a lot to throw at you. There's all kinds of symbols and names and meanings. Fortunately, this isn't physics class where we're going to use them over and over and over ad nauseum. Although then you would eventually be comfortable with it. So anytime I use that symbol delta, it's going to mean the final value of whatever the symbol is after it minus the initial value. X means position. X marks the spot. So the units for speed are meters per second. Meter, I believe we talked about the unit. Remember, I'm teaching physics at the same time. I can get the two confused. Meter is a standard unit of distance. How long is a meter? This is actually how long 2 meters is right here. So a meter is half of this. So a meter goes from here to here. It's the unit we use in science for distance. Yeah, no, I did talk about distance units, so we should have talked about that. Okay, so that's speed and velocity. Let's go on to the next one. We had acceleration. If you look at the equation I just wrote, how do we say that in regular old English? Okay, the acceleration is the change in velocity over change in time. It's a vector, right? Because it has arrows over, that means it has direction. And so it's going to have units of speed was meters per second. Time is seconds, so it's meters per second, right? It's the rate at which speed is changing, which we usually write as meters per second squared. Now, I'm a physicist. I say meters per second squared just rolls off the tongue. But often people say, wait a minute, what's a second squared? There is no meaning to second squared. What it means is meter per second, but mathematically that comes out to meters per second times second, or meters per second squared. So you have to kind of keep in mind that meters per second squared has a very specific meaning, even though second squared doesn't have a meaning. So that's the unit of acceleration. The unit for mass, and I'm just going to put it like this, it has units of kilograms. That's what Russell's comment reminded me. I hadn't defined the units. The kilogram, the standard unit of mass. Kilo means 1,000. So the standard unit of mass is 1,000 grams, not 1 gram. And so if I go to the moon, mass is a measurement of what, how much I made of, so it's not going to change. I'll have the same mass. So one of the things that can be really confusing is we have scales that will weigh you in pounds. Perfect. Pounds is a unit of force. We have others that will, quote, weigh you, end quote, in units of kilograms. Not perfect, because it's measuring your weight, and then it's calculating how much mass you must have for that weight. And the conversion between mass and weight depends on where you are. If I go up to Pikes Peak, I will weigh a very small amount less. Now, it's a small amount. It's not like I'm going to weigh 10 pounds less. But I will weigh maybe a half a pound to a pound less if I go to Pikes Peak without losing a single gram, because I'm farther away from the center of the earth. So the unit there, kilogram. How do you define what a kilogram is? There is a piece of platinum iridium stored in a double vacuum chamber in France. That's the definition. We don't have a good standard for that. And then we have, finally, force. So I'm writing Newton's second law, force net is mass times acceleration. It actually is a vector equation. And so if you look at the units of that, that's going to be units of kilograms for mass times meters per second squared for acceleration. So the unit of force in science is a kilogram meter per second squared. We use it so often that we give it another name, and we say it's a Newton, named after Sir Isaac Newton. There was something to do. Oh, yes. So when I weigh myself on a scale, it tells me my weight in pounds, not newtons. Pounds is the imperial system, or we like to say the English system, although in England they don't use the imperial system anymore. They use the metric system. Technically, back when I was in grade school, the United States changed to the metric system too. When I was in grade school, we started learning about meters and liters and Celsius, and they changed all the road signs on the freeways. So they said this many kilometers per hour and this many kilometers to the next town. Do you guys know that? They did that when I was a kid because the United States officially moved to the metric system. But in shame that we will never live down, the American population said, this is confusing. I don't know what a kilometer is. Gas was, dispensed in liters. I don't know how much gas I'm putting in my car. And so they'd already spent millions of dollars to change all the road signs, and they said, booey. Everybody's confused. Spend millions of dollars to change the signs back.
Yeah, the United States only like 1 in 3 countries.
It's something like that, yes. And if you watch Big Bang Theory, you might have seen Sheldon rail against Jimmy Carter for giving in and changing back to using the imperial system.
How long did that last?
I think only about 2 years. So like 3rd to 5th grades. Yeah, not very long. So we measure our weight in pounds. Pounds are the imperial unit of force. Mass. If you measure mass, you measure in kilograms. That's the metric unit for mass. There has to be an imperial unit for mass. The imperial unit for mass is the slug. So you could say I have a mass of, let's say, 60 kilograms, clearly not me, or X amount of slugs. And the unit for the pound is broken down into slugs feet per second squared. Right, that's what a pound is. Whereas the Newton is kilogram meter per second squared. At least the imperial system and the metric system can share time. Nobody disagrees about that time. Oh boy, a lot of crazy things here. Back to Newton's second law. Why is this important? Well, let's think about something simple. Somewhere here I have a tennis ball. Did I put it away? Yep, I put it away. That's 3 balls here. A tennis ball, a ping pong ball, and an iron ball. If I take each one of these, I put it on my hand, and I flick it with my finger, which I'm going to obviously start with this. So I flick it, what's going to happen?
It's gonna fly off.
Okay, fine, right? What's going to happen if I do the same thing with the tennis ball?
It's just not gonna go as far.
You're right. What's going to happen if I do the same thing with this?
You're gonna hurt your fingers.
I'm going to hurt my finger, so I'm not going to do it. That's right. We all have a practical understanding of Newton's second law. Because the thing with my finger was essentially putting the same force on, it'll put more force on this because it's hard to make it move. And we won't go through that right now. But essentially it was putting the same force, but something with a smaller mass, like a ping pong ball, for that same force, it accelerated a lot more. Its speed, when it left my finger, was much higher because it has a smaller mass. So if you look at the second form I put there, the A is force net over mass. Something with a small mass will accelerate much more rapidly. Something with a big mass won't accelerate as rapidly. And that's why it would hurt my finger. I'm glad you guys said that so I didn't have to, Yeah. That wouldn't be fun, right?
I mean, you still can. I won't stop
You won't stop me.
Don't think anybody
I
does.
appreciate your support.
You're an independent person.
I am. So Newton's second law tells us how things respond to forces, which is really important because, in the end, our entire universe is things responding to forces. Newton's third law, true story. One of the worst dates I've ever had. One of the worst. I took my girlfriend up to Riverfront Park in Spokane. We went ice skating. And so I was totally geeked out about explaining Newton's third law to her. Because, here I am, a physics graduate student, show off a little knowledge, right? So Newton's third law says for every force there's equal opposite force. What that means is if I punch Russell in the arm, I put a force on him. But he put an equal force on me in the opposite direction. And so if I punch him really hard in his shoulder also pushed really hard on my hand. Now his shoulder's softer material, it's probably going to hurt more because it's going to mash up that soft material more than it's going to mash up this little flesh over my bones.
Or you also got to worry about the bones behind it.
I do. If I do something stupid like punch him in the forehead, that forehead is hard. And it'll probably hurt me worse. But the force of my fist on his forehead would be the same as the force of his forehead on my fist. Or, funny thing you see in movies. 2 guys are fighting and one of them will headbutt the other, and it just grab them, boom, they'll hit foreheads together.
It's the worst.
It's the worst, yeah. Because what are you going to do? You're both going to have massive headaches.
Never hit by this mode.
Never headbutt anybody. That's, okay.
Never jump up and punch somebody either, because then you're not going to.
Actually,
Yeah, 'cause you're there.
the secret to when people are playing soccer and the ball hits them, you don't want the ball to hit you, you hit the ball.
Yeah. That's the one thing about the headbutt is the person who's doing the headbutting will have all of his muscles tight, and so his head's not going to go, whereas the other person's head is likely to go bouncing back. And then you have the old coop thing, the brain hits the front of the head and then bounces back, hits the back of the head. My nephew played football last October, He got hit in the head and hasn't been able to go to school since.
Wow.
Yeah, it slays me. He had a perfect score on their little Iowa test against Sawyer. They haven't been able to go to school since. That's the coup counter-coup thing. Got hit here.
Football's one of the worst things for you.
I feel that way now.
That's why they should play rugby. That's why they should play rugby.
Did you watch the Olympics in rugby? They don't even try to tackle each other. They just hold on to each other and hug each other down.
Yeah.
But let's get back on track. So, one last thing about the headbutts, back on track. So, if you actually have to headbutt somebody for some really strange reason,
Do the headbutt first.
you put the top of your head into the point of their nose. Because this is hard, this is not.
4 pounds of pressure.
To break the nose?
Actually, the best place to hit someone with the fist is the chin.
And if you're gonna hit somebody in the nose,
Or the
use
temple,
your
if you
fist,
want to.
use the palm of it.
If you're trying to kill him,
I'm not going to go any further on this. I don't want to kill a man. Okay.
but if you're trying to knock him out,
Skating, that's what happened.
Yes, so what happened when I was ice skating? It was the worst state ever. Almost.
did you hit yourself?
No, so I'm there and I explained to her, okay, so we're going to stand here next to each other, and then I'm going to push, and we'll go off. And what should happen is the force will be the same that I'm pushing on her, she's pushing on me. But because we have different masses, Newton's second law says the one with the smaller mass will have the bigger acceleration, so she'll go off faster and I'll go off slower.
You won't go fast.
You push it down to the ground and shit. Exactly.
She fell down, she starts crying and upset. Wow. And then to make matters worse, we take off the skates and my skate is full of blood. And I take off my sock and it's not mine. They invented me a skate that was filled with blood from somebody else. It was a really special game.
Okay, so what's the worst thing?
Huh?
What was the worst thing?
I think that's good enough right there. We won't go to anything worse.
Okay, I mean, because that's pretty bad.
Yes, it is pretty bad. So that's what this is supposed to be illustrating here. The idea that because of Newton's third law, when you push on something, it pushes back with exactly the same force, but the opposite direction. And Newton's second law tells us that the acceleration is the net force divided by the mass. So when two things interact, the lighter one is going to have a bigger acceleration than the heavier one. And so that's why, for instance, we can already start to understand the moon goes around the Earth. If you want to be real technical, the Earth does a little bit of motion as well. It's not stationary, but it's so much more massive than the moon that the motion of the Earth is pretty small. Likewise, we say the Earth goes around the sun. Well, the sun moves. It moves a fair amount, not as big as the radius of the sun, but it moves about because of that orbit as well. Yeah.
And then the sun goes around the center.
Hmm?
And then the sun goes around the center.
Yeah. And so when you have two objects, you can actually accurately say that they orbit around what we call the barycenter, which is the center of the mass.
No, not that center. I'm talking about the center of the galaxy.
Oh, yes, that also is true. Okay, so I'm going to actually finish up by talking about Newton's law of gravitation. I won't get to use this demonstration until next class period. This demonstration will be really fun for me. Newton determined that there is an attraction between all objects. So every object, every book, every person, they're all attracted to each other. Never repulsive, always attractive. And he further determined that the force, the strength of that attraction, was proportional to the masses. So if you were going to say, so how strong is the attraction between Russell and me? You'd say, well, it's proportional to my mass multiplied by Russell's mass. So if we take the force between me and Russell compared to the force between Russell and Hannah, if we're the same distances apart, the force between me and Russell is much bigger than between Russell and Hannah because my mass is bigger than Hannah's. It's also inversely proportional to the separation squared. Inversely, that's 1 over. And so what that means is when things are closer, the force is stronger. When they're farther away, the force is weaker. And because of that square, if you double the separation, the force is 2 squared is 4. So 1/4 is big. So forces get much stronger when things are closer, much weaker when they're farther away. And so that is his law of universal gravitation. You know the whole story about the apple falling on his head? I'm sure I mentioned not necessarily true. Probably didn't happen. Although, if you go to England, you can see the tree that the apple fell from, both at the college he wasn't at when he made his discovery and his grandmother's home, 2 different trees. And since it's not a true story, you can easily claim that any tree is the tree it fell from.
Well, as long as it's apple.
Yeah, as long as it's apple. Although we can go to the Bible, Eve picked what kind of fruit? Anyway, so the whole idea of that was that there was this gravity, this force at a distance that made the apple fall. And then the last thing, remember I said I'm going to end on this. The last thing then is, what about the moon? If there's a force that is from the earth, a gravitational force pulling the moon to fall toward the apple to fall toward the earth, then there should be for the moon. So the moon should fall and hit the earth.
Isn't the moon slowly getting further and further away from us?
It is, but that's not our point right now. And so Newton said, well, let's think about this. If I have a ball and I roll it off the table slowly, it just goes a short distance before it hits the ground, right? But if I roll it off the table more quickly, you obviously know more quickly what's going to happen. It falls farther away.
Oh, that's right.
So he said, wait now, we have known since well before the time of Christ that the earth is a ball, that the earth is a sphere. And so that means if something goes flying and you're on a sphere, the sphere is curving away from it. And so if it falls, if it's going fast enough, it can fall more slowly than the curve and actually get farther away. If it's going more slowly, it can follow the same rate as the curve and just go around in a circle. If it's going even slower, it will actually hit the surface. And so that's how he was able to explain how the moon orbits the earth without ever hitting it. It's falling constantly toward the earth, but never getting closer. And that's where I'll have to pick up next time. Have a great long weekend, a great Sabbath. I'll see you Tuesday for